those who have come, I'll have to regret that the video quality today is very, very bad. The internet connectivity is very bad, and once in every 2 minutes, the connection is, say, we are getting bad connection. So might be I'll have to call off the class today. And if you are following me in the group, then I will let you know when the next class will be there. So those who have come for the class, yeah, Adit, good afternoon. But the connection today is very, very bad, very bad. So because for the last 5 minutes I have been Alicia, Anhad, good afternoon. The connection is not good today. So we can try till the time it allows us to study, we can try, but then be mentally ready that the class might be called off today. Gauri Priya, Devanshu Sinha, good afternoon everyone. So we are trying to have a class today, but in case the connection continues to remain poor, then we will have this class again on some other day. So let's try as much as possible. And in case there is a disturbance, do let me know through the chat. I will repeat that part which you are not able to listen due to poor connectivity. So far in electrostatics, we have seen that two charged bodies, they exert force on each other. Something like this, which is still hanging here. There are two metal balls, Phet balls, that physics people like to call it. And then we used these straw, tissue paper to create a situation in which a charged rod is brought near to metal balls, and we transfer the charge if we touch it. If we don't touch it, there is an induction. So there is a possibility of it getting attracted. But once they are charged in a similar manner, then later on, there is a repulsion also. We have seen those kind of things, so we won't be repeating these activities for today. But then we tried to understand the cause of these kind of phenomena, and we visualized that around a charged body, the region are, please increase the size of the video, but Devanshu, I'm not showing you the activity. We have seen these activities earlier. Today we are going to learn one new term, electric flux. That will be the topic for today, and for that, say, I need not repeat this activity. In case you have not seen it, I will do it, but that will be towards the end of the class. So we visualized that a region around the charged body has an electric field, and to visualize that, we utilized the simulation by Colorado University, which are popularly called Phet Simulations, and we have seen that as per the convention, that the field around a positive charge is away from it. And I gave you a way to remember it is positive people, they give. Now, these are conventions. Nothing says that it has to be like this or it is this. It's a convention. That which is called positive charge. See, that same thing could have been called negative. It's just a matter of convention. But that which is called positive has a field around it which is away from it. And that which we call as negative charge has a field around it which is towards it. Another thing that we have seen is that more the number of lines, then more is the magnitude. So this is the way to show that if we draw, say for example, if we draw uniform field means the direction is also the same and the magnitude is also the same. So if we draw in a region, if we draw electric field like this, or if we draw electric field like this, say like this, then say electric field here is E1, electric field here is E2, then just by the look and feel of the figure, that's a way of representing electric field. E1 is greater than E2. So if electric field in a region is more, we draw more lines within a region, within an area, a given area, we draw more lines. And if the electric field is less, then we draw lesser number of lines in a given area. Now that is a way of representing. And say if it is a positive charge, then away. If it is a negative charge, then towards. We have seen these kind of things we have seen. If we place a plus q and we draw 4 positive lines around it, say for example, I have a plus q and I am showing field around it and I draw, for example, I draw 4 lines. Now I need to clarify this thing that these lines are not there. Hermoine, Aritra, good afternoon. If I draw these lines around a positive charge, these lines don't exist. It is just a way of understanding. But then the convention is this, that if I place a 2q charge instead of q, if I place plus 2q, then I should draw double the number of lines. Say earlier I was drawing 4 lines, I should now draw 8 lines just to visually give an impression that now the charge is doubled. That is a kind of the convention that we have been using. As I have said earlier, the number of lines, they mean nothing. But this relative number, for example, when the charge became double, then we do double the number of lines. That makes sense. So if you are drawing 4 lines around a charge plus q, then you should be drawing 8 lines when the charge becomes double. This relative number makes sense. But these lines, these drawing 4 lines, 6 lines, 7 lines, that means nothing. But if you are drawing 7 and if you double the charge, then you should be drawing 14 lines. Now that is the kind of the convention that we have seen so far. Now if we have a sphere and as we go away, this is also a concept that we have seen earlier and we are revising. Say for example, you have plus q and around it you have drawn, say, some kind of electric field. Then if you see this region as 1 and this region as 2, then you see as you go away, your the magnitude of the electric field, that reduces. Now, even though the magnitude reduces, you have a issue at hand, and that's for that reason I'm giving you all these introductions, revising these kind of things. See, at 1 and at 2, as you move away, your electric field reduces with 1 by r square. So electric field at 1 is greater than electric field at 2. How do you represent that? How do you represent that? Now, in the simulation that we used, in this simulation, if you place the sensor, then sir, the video is lagging a bit. Yes, Adit, I know. I told you right in the beginning that today the connectivity is very poor. And if we are able to hold this class, fine. Otherwise, we will have this class again. Connectivity is very, very poor today. So in this one, we saw that if you move it closer, the size of the arrow increases, visually giving you an impression that the value of electric field is increasing. And as you move away, the size of the arrow reduces, visually giving you an impression that value of electric field is reducing. But note one thing, and let me move back to this diagram, and let me change the color of the pen now to bring that effect. If I draw a sphere around it, a closed surface around it, then even though, and suppose I have a sphere at a nearer distance, even though the value of E, electric field, is reducing, that number of those number of field lines, you get help, welcome. The number of field lines passing through the sphere, that remains the same. Now I am repeating it at the risk of getting you irritated that why I am repeating the same thing again and again, because it needs to be repeated. As you go, see these lines, they mean nothing. I said if you are drawing 4 lines for a Q or you are drawing 7 lines, they mean nothing. But something which has a sense, which is sensible, is if you are drawing 4 lines for Q, then for 2Q you must be forming 8 lines. So 4 and 8, double, becoming double when the charge becomes double, that has a sense. What is the sense? That it is giving you a visual impression that electric field is more. But try to understand the issue. As you move away, electric field reduces. So one way of seeing is that the gap between the two field lines, it increases. Field lines are now further apart from each other. That is one thing that you can see. In that simulation, you saw that as you move away and the value of field decreases, the size of that arrow reduced. One thing that is not changing is if you draw a sphere here, or you draw a sphere here, or you draw a sphere here, the number of field lines passing through that sphere remains the same. And that brings us to one more term, so that we start understanding what is happening. We start understanding the way we visualize. Not that you are understanding, say you are creating something fictitious, but you start understanding the way we visualize the region around the electric field. And that term is called flux. Here, electric flux. You will find, you are in 12th, those who are studying this chapter, you have seen this term in flow of fluids. Once again, at the cost of repeating again and again, here nothing is flowing. Nothing is flowing. A charge kept around it, nothing is flowing. In fluids, when you use the word flux, liquid is flowing. Here there is nothing flowing. It is just a way to understand the region around a charge. So this quantity, as you are moving out, this quantity, that number of lines, there were 8 lines passing through this sphere. If you draw a bigger sphere, still the number of lines passing through that sphere is same, 8. This gives us one term which is not changing as the distance is increasing, and we call it electric flux. So one way to define electric flux is the number of lines. Now those who are actually understanding it, they would say, sir, what kind of rubbish is it that on one hand you say there is nothing like electric lines, and another way you are saying it, one way to define electric flux is number of lines. Yes, that's the way we understand. That if you can represent it by lines, if you can represent electric field by lines, then those number of lines that you have drawn to represent some particular kind of field, that number of lines, we call it electric flux. So if you see, you can't change now this. If you have used, say for Q, you have used 4 lines, for 2Q, you are using 8. Now for 3Q, you will be using 12 lines. That is a convention that we have used. But then those 12 lines, whether you draw a sphere here, or you draw it here, or you draw it here bigger, that number of lines will not change. So one way to define electric flux is how many number of lines are passing through a surface. Now let's come to second way of understanding something. If I draw some area here, don't get mad at me, like latitude, longitude. Latitude, longitude are imaginary lines which give you a location on the globe. Way to understand where you are, yes. Convention, yes. Because which longitude is 0 and what is 180, whether you increase this way or that way, these are conventions. Okay, if I draw an area, now you can see through this area, two lines are passing through, and we have seen one of the way to define electric flux is how many number of lines are passing through that area. So two lines are passing through it, your flux is 2. If I turn this area, that instead of say this area, say electric field is from my left to my right, and I put this some kind of surface in front of it, and say two lines are passing through it. Okay, now if I turn this area like this, no line will be passing through it. The lines will be going along the surface, but they will not be passing through the surface. Same electric field. Just because the area where I was counting the number of those electric field lines, I have turned this area like this. Now at the same place where two lines were passing through this area and I said electric flux is 2. Now if I turn it like this, there is no field line passing through the area. They are going along the area, but they are not passing through that area. So it means when I say how many electric lines are passing through a surface, I need to present that term as a dot product of E and A. E and A. So let me try and do that. Say this is your electric field. And if the area is in front of it, say something like this. Say this electric field is along X. So let me name this field something. Say 5 along I. And this area is in the YZ plane. So if 3 lines are passing through it, my electric flux is 3. Now, because if I turn this area, if I rotate this area by 90 degree, then my flux becomes 0. So I need to get this electric flux in a different term, and we define that flux as a dot product of E and A. E and A. Now, those who are understanding, the straight away you will have a question: is area a vector quantity? It is. Area is a vector quantity having magnitude of this much, that length into breadth, whatever is the area, and the direction is perpendicular to area. Now, perpendicular to area, there are two perpendiculars. See, if you have a surface, then there are two perpendiculars to the surface, up, down. In general, whenever you are talking of outside, you take that as positive. So now outside will have a sense only if you are enclosing a charge. Let me redraw it and explain it with a considering a charge. Let's say I have a 2 microcoulomb charge. If I have a 2 microcoulomb charge and there are field lines going out of it. Field lines going out of it. Now, if I let me change the color. If I draw a closed surface, then the first definition that we saw, the flux will be 1, 2, 3, 4, 5, 6, 7, 8, 9. The flux will be 9 because first definition that we gave for electric flux was how many number of lines are passing through it. Now, if we take an area here, if we define some kind of area here, the number of field lines passing through this area, there are two. And if I add up, then this whole sphere which is encircling it, the total flux will be sum of this E into A, these number of lines like this. Now, because there was an issue with the turning, if the area is not perpendicular to the field lines, and if you turn that area, then no field lines is passing through it. So we defined electric flux as E into A. And if you see that how much is the field lines passing through it, the total flux passing through that total surface area, if you see, the total surface area of a sphere is 4 pi r square. The value of field at any point is 1 upon 4 pi epsilon naught q upon r square. Now, if you see how much is the total flux, you will see that the total flux is q upon epsilon naught in this case. That brings us to the third definition of electric flux. So we have three definitions of electric flux. Let me give you a summary and bring you to some questions. Three definitions of electric flux that we will be using, and at different positions, different situations, we utilize different definitions. One is how many number of field lines, and this definition is more beneficial for comparison purposes. For example, the flux becomes double, then basically means that you draw twice the number of lines, and we have seen its utility. The second definition is the dot product of E and A, and we defined that area perpendicular outside area to be positive. That also gives us the sign of flux. If the charge inside is positive, coming back to this one, if the charge inside is positive and this E and this is your A outside, this is your E, and E and A, these, say in this case, E dot A is E A cos of 0, and this is coming out to be E into A. Let's take just these some numbers. Now, with a positive charge, the field is out. So this gives us one thing, one sign, that flux outside, we take it as positive. So few conventions which are developing, if the flux through a closed surface, field lines are going out, we take that flux as positive, the sign of flux. If you come to this one, say total flux came out to be the Q charge enclosed upon epsilon naught. If Q is positive, you see that flux is also coming out to be positive. So the conclusion, or say the sign convention that we are having is, if you have a closed surface, how many number of lines are passing through it? That is one definition. E into area, and more precisely E dot A, that is the second definition of it. And the third one that we are getting is, this one is a general case. We have done it in one particular case where a charge, point charge is enclosed by a sphere, but this is a general result. General result means what? That any closed surface, if it encloses a charge Q, the total number of field lines passing through it, or say the total flux passing through it, is 1 upon epsilon naught times the charge enclosed. This is the Gauss theorem, which we will be using later on quite a lot. Gauss theorem, that the total flux passing through a closed surface is 1 upon epsilon naught times charge enclosed by that surface. So just to sum up before we move on to some questions, three ways to define electric flux. One is how many number of lines are there. Second, dot product of E and A. And we saw why we need that dot product, because if you turn that area by 90 degree, no electric field lines passing through it. If you turn it like this, electric field lines are passing through it, so flux is passing through it. And the third one, which came out as an application of it, is that the total flux passing through a closed surface, if it is enclosing a charge inside, is 1 upon epsilon naught times charge enclosed by that surface. Now let's try out in some questions. Uh, Easy, simple questions. We will start with NCERT. We will do some questions which were asked in CBSE also, and then we will move on to some questions from HC Verma in this topic. So NCERT, consider a uniform electric field of this much, and I means this is towards x-axis. What is the flux of this field through a square? All these are given in the course which we are following on anytimeteacher.com. If you go to academic courses, 12th physics, you will get electrostatics. In electrostatics, this is 1.10 because this course is mapped to NCERT. So this is 1.10 of NCERT. So NCERT 1.15, this electric field is towards the x-axis. I means towards the x-axis. What is the flux of this field through a square of 10 centimeter, just 10 centimeter on a side? So means 10 centimeter into 10 centimeter. That is it. Just remember, centimeter is not your unit. You have to convert it into meter square. So what is the flux through a square of 10 centimeter side whose plane is parallel to the YZ plane? So value of E multiplied by the area, because it's passing through it. And what is the flux through the same square if the normal to its plane makes an angle of 60 degree with the x-axis? So E dot A, E into A into cos of 60, that would be your answer. Easy one, easy one. If this plane, I said just a word of precaution, that this 10 centimeter converted into meter. If this plane is parallel to x-axis, if this plane is parallel to the x-axis, the flux passing through it would be zero, because all the electric lines would be passing along the plane and not into the plane. Let's move on to the next question. NCERT 1.16. What is the net flux of the uniform electric field of exercise 1.15, this one, through a cube of side 20 centimeter oriented so that its faces are parallel to the coordinate planes? What it means is that you have these coordinate planes. There is a cube placed here. A cube placed here. Now the electric field was along x-axis. Now we had a convention, flux which was out was positive. So flux which is into a surface, that would be negative. Now if any field line, because E was like this, towards x-axis, any field line which enters here will also will pass through it and will ultimately come out too. So if there are say 5 lines which are going into the cube, 5 lines will be coming out also. So going in, if you say minus 5, those who are going in, and which are going out plus 5, the net flux will be 0. Easy one. Whatever is the size of the cube. A charge Q is placed at the open surface of a cylinder which is closed from the other. And this is a popular question. CBSE has asked it. In HC Verma, there is a variation of it. So let us discuss these two questions, the hemisphere wala question and the... Now, the third definition that we saw, flux passing through a closed surface, flux passing through a closed surface is 1 upon epsilon naught times charge enclosed by that surface. Okay. So let's say there is a sphere. Let's say there is a sphere and there is a charge Q placed at the center of that sphere. So if I cut it open, you will have something like this above and you will have something like this above. Say down, there will be two hemispheres kind of thing, and you have a Q at the center. This will be an enclosed surface. The total flux which passes through this sphere, the total flux means total number of field lines which passes through this sphere. This flux is 1 upon epsilon naught times charge enclosed. So it will be Q upon epsilon naught. Now, how many of these are passing through this part? How many of these are passing through this part? Common sense says half are passing through here, half of the flux, and half of the flux will pass through this because there are only two halves of a sphere. So half will pass through this, half will pass through this. So if there is a plus Q, say Q kept at the center, through half of the sphere, flux passing through will be 1 upon epsilon naught times charge enclosed half of it. And likewise, Q upon 2 epsilon naught, this much of the flux will be passing through the lower half. We can use Gauss law. Yeah, Gauss law, we will use it for some other purposes also. Yeah, Gauss law has actually come from this discussion. Abhinav, Gauss law today, Gauss law has come as a consequence of those definitions. Okay, if instead of a sphere, I have a long cylinder, and at the center of this, I place a Q. Now, due to this Q, field lines will be passing through all sides, like this, like this, like this, like this, like this. But then common sense says half of these lines will pass through this one, and half of the field lines will pass through the half of the part of the cylindrical. So whatever is the shape, the flux passing through, flux through half of the cylinder will be half of Q upon epsilon naught by saying Q by 2 in Vanshaj, yeah, right. Now this concept is utilized in some questions, and I will pick up those questions now. See, for example, instead of a sphere or instead of a cylindrical shell, suppose I have a cube, and at the center of this cube, I place a charge. At the center of I place charge Q. The total flux passing through this cube, is 1 upon epsilon naught times charge enclosed, Q upon epsilon naught. Now, if this Q is placed at the center, then this flux will be equally divided, equally passes through each of 6 faces of cube. The cube has 6 faces. The charge is placed at the center. So by symmetry, by common sense, the total flux which is coming out of this charge, the total field lines which are coming out of this charge, they should pass equally through each of these 6 faces. So flux through each face is 1 by 6 of Q by epsilon naught. Now this is common sense. This is easily understandable. The question which has been asked by NCERT and is a common question is the little modification of this question. They say there is a square of side A, and at a height of A by 2 from it, there is a charge plus Q placed at a height of A by 2 from it. And the question asked is flux through square. Flux through this square, how much is it? Now, can you see that this question and this question, they are exactly same. If I say this is a cube of side A, if I say this is a cube of side A, side A, then do you see these two questions are exactly same? Each face of this cube has sides A. It's a square of side A, and the charge is placed at a distance of A by 2 from each of this face. So do you see these two questions are exactly identical? But the same concept, if you take it a little bit further, if you stretch it a little bit further, it makes things even more interesting. Let's do that. Say if one of the questions says that there is a cube, uh, say cube, and at the corner of the cube, a charge is kept at the corner of the cube. How much flux passes through this cube? How much flux passes through this cube? I'll have to change the color even more. What you do is you enclose this charge symmetrically. Now, if you place on the side of it, you place one cube. On these sides, you place more cubes. Now, do you see? This charge has come in the center of 4 cubes. And on the upper surface of these 4 cubes, you have placed this charge on the upper surface. Now, over it, if you place, let me change the color even more. Something like this, so that I have a different surface. Now, over it, if you place 4 more cubes over it, 4 more cubes over it, 4 more cubes over it. Now, I'm trying to change colors as much as possible so that you can visualize. Now, do you see that this charge has come at the center of a, yeah, very good, Abhinav. That 4 here and 4 above it, out of these, this charge is at the center. It is surrounded by 8 similarly placed cubes. This charge is placed at the center of 8 similarly placed cubes, 4 down and 4 over it, this yellow color. So the flux through each one, flux through each cube is 1 by 8 of Q by epsilon naught, because total flux is Q by epsilon naught. Now let me change the question a little bit. If you understand it, it becomes fun. Suppose the charge is placed here. It's fun to see how do you symmetrically enclose it. You place one here, you place one cube here, and you place one cube here. You have to enclose it symmetrically. And then you see how many cubes do you require to enclose that charge symmetrically, divide that flux equally amongst them. So a few simple ones that we have done. Let me see some more questions from NCERT and from CBSE that has been asked. These are the ones which are common ones. All these questions that you see, this is that question from NCERT. The same question has been asked by CBSE also. Now, another question which is very popular is that a charge, that depends on where do you place it, Aritha. Another popular question is that you have placed a charge and the electric flux passing through, just a second, that you have placed a charge plus Q, and around it you surrounded by, and the flux passing through this is, say, phi naught. If you double this radius, how will the flux change? Now this question just wants to check one thing. If you increase the radius, if you have a second surface of double the radius, say this surface, the value of E here and value of E here, that is different. But then the flux, which was number of field lines that you draw to represent around it, that does not change. So if you have another surface whose radius is twice of this one, this radius, the flux remains the same. Flux passing through it remains the same. There are few more simple ones which are given in H.C. Verma. I have given you the reference, some additional questions from H.C. Verma, page 141. Try doing it, because if you are able to do these, this is a simple topic, easy topic, but if you are able to do these questions, which are easily doable, then when we apply Gauss theorem to find the electric field due to various charge distributions, there the life becomes much simpler. So see you again next Tuesday. Luckily, we were able to run this class. I was not very much hopeful that this class I'll be able to conduct this class because of bad connectivity. See you on Tuesday at 12:30. And in the meantime, try to do all these questions from NCERT and some of those additional ones from H.C. Verma. You will find this topic is easily doable. You can master it easily. 3 definitions, 3 ways that we have defined electric flux. One, the number of field lines. The second one, E dot A. And the third one, by using, which becomes the Gauss theorem, that flux passing through any surface is 1 upon epsilon naught times charge enclosed by that surface. Aritra, sir, for symmetry, should we every time form a cube or any symmetrical figure? Remember, Aritra, let me answer this question for you, that we have answered it here. See, here it was a spherical surface, symmetrically enclosing, and flux passing through each hemisphere is half of q by epsilon naught. Here, we enclose it with a cylindrical surface. Both these halves of the cylindrical surface, the flux passing through them is half of q by epsilon naught. So you place it in a way that the charge is symmetrically placed, so that you can divide that flux equally amongst all those surfaces. Enclose that charge in a way that the flux gets divided equally amongst those surfaces, amongst those bodies which you are putting around. So see you again next Tuesday, 12:30. Thank you so much for being in the class. Bye bye.